So we have been learning about pacemaker cells and how pacemaker cells are located in the conduction fibers within the conduction system. And we keep mentioning that these pacemaker cells generate action potentials. And so what we would like to do now is look at this pacemaker activity. When you look at this graph, there's some important terminology for you to understand. We use the term pacemaker potential loosely at times. The pacemaker potential is actually just the graded potential of the pacemaker activity. Numbers 1 and 2 here, technically, are called the pacemaker potential. However, it's very common for researchers and physiologists to call the entire graph a pacemaker potential. And so I try my best to only talk about the pacemaker potential in terms of this graded potential. However, that doesn't always happen. And so since it's a common occurrence amongst physiologists, if I say pacemaker potential, this may include the entire action potential as well. When these pacemaker cells generate these action potentials, remember that they're traveling through the conduction system. And when they travel through the conduction system, they can also travel to cardiac contractile cells. And they can travel to those cardiac contractile cells via what structure? Gap junctions. Okay, so let's take a look at this pacemaker activity. So first off, the first thing to note is that the resting membrane potential is somewhere between negative 60 millivolts and negative 70 millivolts. So the resting membrane potential we say is unstable. And the reason we say it's unstable is that the cell does not stay at rest for very long. It's a very short term that the cell is actually at rest. So let's look at the phases of the pacemaker. I started you off with phase 4, which is repolarization. So the number on your slide is the same number indicated on the graph. So step 4 here is repolarization, something that you're very familiar with. Steps 1 and 2 are part of the pacemaker potential. They are the graded potential. Number 1 is the first part of slow depol, and number 2 is the second part of what we call slow depolarization. So when we talk about slow depolarization, that is strictly includes only numbers 1 and 2 on the graph. Number 3 on your graph is what we call rapid depolarization. Let's look at threshold. We've talked about threshold in a neuron before, but now we're talking about threshold in a cardiac cell. Threshold in a cardiac cell, and a pacemaker cell specifically, threshold is at negative 50 millivolts. So everything we're referring to here is happening inside of a pacemaker cell. So what I'd like to do now is go through each of the phases of the pacemaker and look at what channels and what ions are moving and therefore causing these various phases. We'll start with repolarization. In repolarization, just like in a normal neuron, the voltage-gated potassium channels are doing what? Hopefully you said they're open. Remember, at the peak, they're open, and as you go through repol, more and more of them are open. So through the open voltage-gated potassium channels, which way does potassium move? Do we have potassium influx or potassium efflux? Hopefully you said that we have potassium efflux. Remember that potassium is moving along its electrochemical gradient, so it's moving out of the cell. Keep in mind that the equilibrium potential for potassium in this pacemaker cell is the same as if it was a neuron, so negative 90 or negative 94 millivolts. So also during repolarization, we have a new type of channel to briefly introduce you to, and I'll talk more about it in a few moments. In repolarization, the voltage-gated L-type calcium channels are closing. I'll return to those L-type calcium channels shortly. After repolarization and the cell reaches rest, and remember it doesn't stay at rest for very long, and the reason it doesn't stay at rest for very long is because of a new type of channel called a sodium funny channel. And I didn't make that name up. It's true. It's called a funny channel. And the reason physiologists named it a funny channel is because it behaves differently. It doesn't behave like a voltage gated channel in the sense that it doesn't open in response to a change in a membrane potential. Instead, it responds to repolarization. And so when I say it responds to repolarization, what I mean is it's going to open. So it's opening during this first part of slow depolarization. When it opens, it's only open for a brief moment in time. So it opens and closes, opens and closes, opens and closes. Very quick, open and closed. So when it is open, which way does sodium move? Do we have sodium influx or do we have sodium efflux? This is like a regular neuron, and so you will have sodium influx. So sodium is moving along its electrochemical gradient. But again, it's very important to realize that when this funny channel opens, it closes, open and closes very quickly. When you look at phase 1 on the graph, look at how short it is. And the reason it's so short is because of that channel opening and closing. Now, while this is happening, your voltage-gated potassium channels are closing. So now let's continue on with our slow depolarization. We have finished the first part of slow depol. When we have sodium influx, did that change the membrane potential? The membrane potential became a little more positive, correct? So because we had a change in the membrane potential, and this change in the membrane potential triggers a voltage-gated T-type calcium channel to open. Now, the T stands for transient. So what this means is this is kind of like the sodium funny channel, where this channel opens and closes, opens, closes, opens, and closes. So again, look at phase 2 on your graph and look at how short this second part of slow depol is. Because the membrane potential is becoming more positive when the T-type calcium channels are open, do we have calcium influx or calcium efflux? Remember that calcium is going to be moving along its electrochemical gradient as well, and that direction is into the cell, or calcium influx. Remember that the equilibrium potential for calcium is positive 130 millivolts. That will be important. The voltage-gated T-type calcium channels, when they open and then they close, this is enough to get the membrane potential to threshold. So at negative 50 millivolts, we are at threshold, and now, because we've had a change in the membrane potential again, another voltage-gated channel is going to open, and this one is called the voltage-gated L-type calcium channel. L stands for long-lasting, meaning that it's open for a much longer period of time than the T-type calcium channels are. So this voltage-gated L-type calcium channel, when it opens at negative 50 millivolts, you have calcium influx. And so positive charge is moving into the cell, and that's what creates the rapid depolarization phase of the pacemaker. Once the peak is reached of this action potential, then the L-type calcium channels begin to close, the voltage-gated potassium channels are open, and you have potassium efflux, and hence the membrane potential becomes more negative. And so it's very important for you to be able to draw a pacemaker, both the pacemaker potential and the pacemaker action potential, to be able to draw it, because there are a lot of scenarios and things that could go wrong with the various channels.